Okay guys, welcome back. We're going to continue looking at limits, although we're going to kind of change gears a little bit. If you remember about limits, some of the important things to remember for limits was when you approach a value, limits only care about what you approach, right? They don't care about the actual value at that point. And that was one of the differences between limits and maybe saying what is the value at that point. If I ask you what is the value at that point, I want to know what the actual value is. Limits care about only what you're approaching. So whether that value actually exists or not, or is something different, doesn't matter. It's only what you're approaching, okay? So what we're doing here is we're going to kind of jump into this new topic called continuity. And if you think about in life in general, if something's continuous or there's continuity, that means there's no breaks, right? So maybe, for example, if you watch a movie continuously, or all the way through, you'd say you watched it continuously from start to beginning. You didn't take any breaks. Okay, so in math, it's sort of a similar idea. Okay, so let's take a look actually at this graph down here. This graph is not continuous. And I encourage you to think about for a second, if I'm telling you the graph is not continuous, could you tell me the x value where this graph is not continuous? What x value would the graph not be continuous at? Okay, where is there a jump or a break or a gap or something where the graph's not continuous? So let's actually, this really should have arrows on it. This graph goes in forever in both directions. And notice that I can trace this entirety of the graph with my pen without ever lifting it up. Right, I'm tracing this entire graph all the way through. Every point on the graph I get to trace. There are no breaks, no gaps, nothing until wham. Right there I get stuck at an open circle. And then if I get to that open circle to trace the next point, I have to pick up my pen, come down to the letter B at that point, then I have to pick my pen up again and continue along the graph of the line. We have that open circle there, right? So because I had to pick up my pen, right, imagine tracing it, right? If I'm tracing the graph with my pen, to trace all the points, once I get here to the letter C, I have to pick it up, fill in B, then jump back up. Okay, that's a really informal definition or a really informal way of proving something that's not continuous. So if you look down at the bottom, I said because we cannot trace the entirety of the graph with our pencil, okay, I should really add without picking it up. Okay, so add that in. We would say that this graph is not continuous. Okay, it's definitely not continuous. And we can maybe even add here the question, where is it discontinuous? Where is there a break? And when we ask this, we're asking for the x value. What x value is the break at x equals 1? So at an x value of 1, right, let me just choose a different color. At an x value of 1, right, you can see we have an open circle and then a hole down below it. Right, so we would say this graph is not continuous at an x value of 1, or it's discontinuous at an x value of 1. Okay, because I had to pick up my pencil, right? If I'm tracing the graph, I had to pick up my pencil or pen to trace all the points. So that's a really informal way of proving a graph or a function to be not continuous. Okay, so graphs can be not continuous, or graphs can be continuous over a range of values, or we could say it's not continuous at a singular point. You could say, where is it not continuous? All right, so let's develop this a little bit further. As I said, that pencil definition of tracing the entire graph is a good way to check, but it's not really a formal mathematical definition. Okay, so let's take a look at the same graph. So if we go to the next page, we have the same graph, but I want to think a little bit more about what makes a graph continuous and what makes it not at a given value. So we know already that the graph is not continuous, okay, at an x value of 1. But I'm going to add something else here. I'm going to say that at an x value of -3, this point right here, the graph is continuous. Right, and clearly you can tell, right? If I'm tracing the graph, I go right through that point without having to pick up my pencil or do anything. I could go right through that point and hit it without a problem. So we would say that the graph there at -3 is continuous, and we already know that at 1 it's not continuous. So let's develop this a little bit further. So I want to think about this in terms of limits. So there are three things that we need to prove or state a graph is continuous. And the first thing that we must say is that the limits as x approaches a, and a just represents a value, the limit as x approaches a of some function must exist. If we're going to argue that a function is continuous at a singular point, this statement must be true. So let's check this out for actually both -3 and +1. Is the limit as I approach -3 going to exist? Does that limit exist? Yeah, that limit, right? Maybe I'll put it up here, right? The limit as x approaches -3 of f of x equals -1. So that checks. Okay. Conversely, does the limit as x approaches +1 exist? Does it equal some value, or does it equal not exist? Well, it equals +3, right? As I come to that x value of +1 from both directions, both those arrows are pointed towards 3. So the green dot is continuous. At x equals 1, the graph's not continuous. So it seems like that can't be the only qualifier, because both exist, yet we know at x equals 1, the graph's not continuous, but at x equals -3, it is. Okay? So just saying that the limit exists at a singular point does not mean that the graph is continuous there. So there must be more things that have to be true. So the second thing that must also be true is that f, let me choose a different color, let's go back to green. The other thing that must be true is that f of a must exist, that there must be a point there. So let's come to the graph in green. Does the point, okay, does this point exist? Yes, it does. There's no open circle at -3, -1. It's a closed circle. Okay. So in 2, does f of -3 equal something? Does it equal a number? Does it exist? It does. It equals -1. So box 1 checked, that checked. Okay. Does f of 1 exist? Let me just go back to red. Does f of 1 exist, guys? Think about it for a second. What is f of +1? Well, f of +1, where's my closed circle? It's there. So f of 1, that exists. So the limit exists, check that. F of 1 exists, check that. So far, all four things I've found out so far have been true. Yet we know the green dot is continuous, yet at x equals 1, that graph there is not continuous. So there must be more that must be true. Okay, and the last thing that must be true is that if 1 and 2 are true, if the limit as x approaches a exists and the value exists, for the graph to be continuous, the limit as x approaches a of f of x must equal f of a. This is basically just saying the limit must equal the value. It's confusing maybe a little bit, but it's a mathematical way of just saying the limit must equal the value. So let's look at the one in green. Okay. Does the limit as x approach -3 of f of x, does that equal f of -3? Is this true? Well, take a look at our answers for 1 and 2. They both equal -1. So yes, this is true. Right? The limit is pointed towards -1. The value is -1. Okay? If both of those are true, you can clearly see I can trace that graph without having to pick up my pencil. However, if we look at the other point, or the x value of 1, I would ask you, does the limit as x approach 1 of the function, does that equal f of 1? Well, the limit is 3, yet the value is 1. That is clearly not true, okay? Because, in this case, the limit as x approaches 1 does not equal the value at 1, we would say the graph is not continuous. Okay? So for a graph to be continuous at a singular point, all three must exist. If any of the three are not true, then the graph would not be continuous. Okay? The graph would not be continuous. So let's take a look at a quick example. Here's what I have. I have the limit as x approaches a, and it's got a little negative, so from the left, right? So from the left, that's what that means, from the left. And then the limit as x approaches a from the positive is from the right. The one from the left equals 3, the one from the right equals 2. Okay, is it continuous at a? Maybe it helps to draw a little graph. We'll call this a. I know as I approach from the left, the limit is 3. I don't know if it's open or closed. It really doesn't matter here. As I approach from the right, it's 2. So, would you say the limit exists at a? No, the limit does not exist at a because the two one-sided limits are going to different places. So the question is it continuous at a? No. And when I ask you for why is it continuous or not, you have to give me one of the three reasons above. We would say no, and this is what you must write. You can't say because I had to pick up my pencil or anything like that. You have to give one of the three reasons. And the reasons it's not continuous is because the limit as x approaches a of f of x equals dne. That is what you must write. Anything else besides one of those three things, you would lose points. Okay, so just be very careful with that. So let's try the next one. And actually, why don't you take a second to think about that one? I'll give you a second, maybe pause the video and see if you can come up with the correct answer and the correct reasoning using the correct notation for why this is continuous or not continuous at a. Okay, so hopefully you paused and given an answer. This one's saying that the limit as x approaches a is 2. The value at a is 7. Is it continuous? Well, hopefully you said no. No, it's not, because the limit as x approaches a of g of x, in this case it's g of x, does not equal g of a. So the limit, right, our reasoning here is the limit doesn't equal the value. That would be reason 3 from the last page. Right, if you're looking at, did it fail reason 1, reason 2, or reason 3? It failed reason 3. Graphically, what does this look like? Right, we'll say it's a. The limit, is 2. However, the value is 7. You can see that if you tried to trace that graph with your pen or pencil, you'd have to pick it up to get to that point above it. Okay? All right, let's try this graph here. It says, look at the graphs below. Are they continuous? Why or why not? Where are they discontinuous? Well, they clearly are discontinuous. And just make a note here that these are open circles at -4, -2, 2, and 4. Okay? So, let's go through this. It's not continuous at several places. So is it not continuous? Okay, let's list all the places it's not continuous. Okay. So where is it not continuous? It's discontinuous. I'm going to try to lump them all together, ones that have the same reason. So it's discontinuous. Let's take care of all the open circles. Discontinuous at x equals -4, -2, 2, and 4. And you can see that if I were to trace the graph with my pen, I hit an open circle, I have to jump over the open circle to pick up back up again the graph. You can't go through the open circle because it doesn't exist. So I clearly had to pick up my pencil in black there. So we can clearly see it's not continuous. What is the reason why? Well, let's take a look at this. Does the limit exist at all these points? Well, yeah, if you were to trace the graph and look at where the arrows are pointed, they're all pointed towards the same place on each one, right? All the arrows are pointed towards the same place. So clearly we can't say because a limit does not exist. Let's go to the number, so since number 1 is true, let's go to number 2. Does the value exist? Well, I see open circles, however, I don't see any closed circles anywhere. So it looks like those values don't exist. So I would say it's discontinuous at -4, -2, 2, and 4, because f of a equals dne. We can just state f of a equals dne, and I kind of know we were talking about those 4 values. Okay, so it's discontinuous there because those values do not exist. Looks to me like the graph is also discontinuous at those vertical asymptotes. Discontinuous at -3 and 3. Now, why is the case? Let's, again, go from start at number 1. Does the limit exist? Well, let me erase some of the stuff here that I drew that we've already covered. Let's take a look. Does the limit exist? Well, let's first come to, let's do the one around 3. As I approach that asymptote on the right, that limit's going towards infinity. However, if I come from the left side, that arrow is pointed down towards -infinity. The limit would not exist. The limit would not exist, and you can clearly see around -3 the same thing is happening. So I'd say it's discontinuous at -3 and 3 because the limit as x approaches a of f of x equals dne. It does not exist. Now you might say, Mr. Bodner, there's no value there. Could I have said f of a does not exist? That is true. You could also say, so you could say this, or, you don't have to say both, you just have to give me one, or because f of a does not exist. If you gave me reason 1 or reason 2, either would be acceptable. Okay? You cannot say, in this case, you cannot say because the limit as x approaches a of f of x doesn't equal f of a. They don't exist. So you can't say things that don't exist are or are not equal to each other. So in this case, you cannot say that. Okay, you cannot say that because they don't exist. So how can you say these two things aren't equal to each other if they don't even exist, right? They don't exist. So you must say either statement 1 or 2. You cannot say that third statement in this case. Okay, so let's do the last one. I would encourage you on this last one to pause the video, do it yourself, and then check your answers back with me, okay? And actually, before I do that, exclude 4. Okay, exclude. Oops. If you already paused it and gave me an answer, that's fine. It's a little bit confusing, so don't worry about the end of the graph there. But all other points worry about. Okay, so let's take a look at where it's discontinuous. I know it's discontinuous. Let's work our way left to right. Here, at -3, okay, it's discontinuous at -3 because, okay, it looks like the limit exists, the value exists. Looks like because the limit as x approaches -3 of f of x does not equal f of -3. Right? It looks like the limit's equal to -1. However, the value is +1. That would not exist. It also looks like that it's discontinuous at x equals -1 and +1 because the limit as x approaches a of f of x equals dne. If you wanted to write that twice and say the limit as x approaches -1 equals dne and the limit as x approaches 1 equals dne, that's fine to say that. But when you're listing the same reason for multiple points, you can just use a as the placeholder. Right? The limit at both of these points does not exist. As I approach -1 from the left and from the right. Those arrows are pointed towards different places, so it does not exist. Same thing for positive 1. Those arrows are pointed towards different values, so that would also not exist. Okay? That looks like to be the only place. Again, at 4, ignore it. So if you paused the video before I said that and you came up with something for 4, that's fine. It gets a little bit technical when you get to the end points of graphs, so we're not going to get into that at this point. Okay? All right, so that is continuity. Okay? It can be a little bit tricky at first, but hopefully you picked up on it a little bit as you went along. Your homework is worksheet number 7. Same deal, work in your groups. Okay, work in your groups, and I think you'll be okay. Okay, so it's worksheet 7. You can find that on Canvas, and we'll see you guys in our next class.